So our topic today would be microscope. Our topic is microscope. And two types of microscope we will be studying, the simple microscope and the compound microscope. Before we get into microscope, let's brush some topics of grade 10 which will be necessary for us. Then we will appreciate this more and it will become easy. So as a human being, okay, as a human being, all right, what we have, this is our say line of sight. Okay, this is our line of sight. So we have something which is known as, what is the range of vision of a human being? All this we have studied in grade 10. The range of vision of a human being, we have two points out here. One is known as the near point, and one is known as your far point. So as a human being, you are supposed to see distinct and clear only between this range. One is a near point and one is a far point. The near point, come. The near point we actually represent by D, and we call it as LDDV, least distance of distinct vision, and that is 25 centimeters. Okay, this is known as my least distance of distinct vision. And the far point is always taken as infinity, right? Least distance of distinct vision. What does this mean? This means, I think then we can switch off the call since you are here already. Okay. Why to unnecessarily make the CPU hot? Okay, so we have the human being's range of vision is from near point to far point, and the far point is taken as infinity, the near point is taken as D, which is the least distance of distinct vision, and this distance is known as 25 centimeters. What does this mean? This means that if I want to see something clearly, very close to my eyes, the closest that I can bring an object towards to my eyes is 25 centimeters. If I try to bring it beyond 25, you can actually do that. Take your pencil and try to read the graphics that are there on your pencil. You will start observing them blurry, and you will immediately be prone to some severe nauseatic or headache feeling. That's why when you go for your specs, they will always give you that you should observe at a close distance, and then in that close distance we always say that how far, that's at an arm length. As an arm length, this is your arm length, and at an arm length you see the highest one. And if you actually bring something more closer to it, at that time you will be seeing something which is the last distance at which you see something clearly. Is this much understood? Okay, so you need a tissue or something? All okay? Oh, fine. Right. Now, microscope. What is the job of a microscope? A job of a microscope is to magnify something and present it to me in a magnified manner. Now, more you understand this concept, your derivations will become absolutely easy. Now, your eye is also an eye lens. So how do you see something magnified? We see something maximum magnified when the object is kept at D. Is this understood? For an eye, so we write, say, for an eye, the maximum magnification that can be obtained is when object is placed at D. D means the distance of distinct vision when object is placed at D. So when your object is placed at D, you see an object the maximum magnified, and it will actually become bigger. Just try to see the pen here and the pen here. The pen becomes bigger when it is brought near our eyes. But beyond that, we are unable to see. But if that particular image is not sufficient for you, that is when your demand for a microscope or a magnifying device is coming up. Are you understanding? So sometimes we have got some some writings that are behind a credit card or something, you're not able to read it. So you switch on either your hand mobile, or you switch on to take a magnifying glass, because at that time, by keeping it at 25 centimeters also, it's not sufficient for you. So let's see some basic of image formation. Okay, let's see a basic of image formation, and this way your concept will become absolutely clear. So let's say this is your eye. Okay, this is your eye, and this is your eyeball or your eye lens or the cornea portion. And let me keep an object now. Okay, let me keep an object. Let's say this is the object. This is the object. Now, how do we see the object? We see the object when actually the object will create something called a vision angle, which we'll try to understand. So there will be a ray which will be coming out of this object and will actually go and hit here. Understood? At this moment, the image of this object is actually created at this place. Right. Here we should now understand something which is known as a concept known as the vision angle. Vision angle. The vision angle is the angle, say the vision angle is theta. The vision angle is the angle created by the object with your eye. Let's say this is theta. Have you understood? And by our discussion so far, we have said that when the object is at D, that is 25 centimeters, at that time, the object size is the maximum that you can see. Understood? Now you yourselves try to apply some analogy. If the object size is more, a bigger object size, don't you think will create a bigger vision angle? Obviously, just apply common sense. If I have a bigger object means we sense it as bigger. So why are you sensing it as bigger? Because a bigger object creates a much bigger angle on your eye. As a result, now the image is up till here. Clear? So from this discussion, one thing we have understood, that height of object is directly proportional to the vision angle. A bigger object creates a bigger vision angle, a smaller object creates a smaller vision angle. And where is your image, beta? Your image is here. Your image is here. And what do you want? You actually want the image to be bigger. You want the image to be bigger. So the image can be bigger only if the vision angle is increased. If you increase the vision angle, then only the image gets bigger. How do you make the image bigger? By placing the object at such a place where I can see the image the biggest as possible. But if that is not sufficient, then what I need something which is known as a simple microscope, which is a hand lens. This is the concept. Okay. So let's go further and we get into something which is known as the simple microscope. Derivations are same in both. If you understand one, the other was a cakewalk. Simple microscope. A simple microscope is also known as a hand lens. And it just magnifies maybe 4 to 6 times, not more than that. Right. So let's see the ray diagram for a simple microscope. Now this is again a grade 10 case. So this is my principal axis. A simple microscope will actually have a lens which has a very large focal length, with a large focal length. Okay. With a large focal length. Means its focus will be quite far off from the lens. Understood? So that when we use a magnifying glass, how do you use a magnifying glass? You will be actually projecting it on the object, so that wherever you keep the object by choice, the object will always take a position where it will be between the focus and the optical center. Is this understood? Let's say this is our secondary focus and this is our primary focus. Okay, let this be F and let this be F dash. and this is 0. This is my object. My object is HO is the height of the object. Clear so far? Okay. Now this is grade, what do you call, grade 10 case. A ray of light parallel to the principal axis will always pass through the focus, right? And another ray, which is actually coming from the object's head and it is passing through the optical center, goes undeviated. Now they become divergent rays. These rays are now divergent rays. So they are not supposed to meet. So what do? We will extrapolate these rays now. So we extrapolate these rays. Okay. And and I extrapolate this ray also. Fine. More or less, not that bad. So you create a erect virtual image, the height of which will be hi. If this is AB, then this is A dash B dash. Clear? The ray diagram is clear. So hand lens, and this hand lens will have a large focal length. Large focal length. Why do you have a large focal length? So that by default, when you project it on an object, the object gets its position between optical center and focus. Large focal length, so that the object always comes between the optical center and the focus. Clear, children? And as a result, you will be getting a virtual and you will be getting a erect image, and it will be also magnified. Now, though you have learned in grade 10 that magnification for lens is equal to V upon U or HI upon HO, when we study about microscopes, we will be not studying it in the linear magnification. What we will bring into play is known as angular magnification, the concept of angular magnification, which has already been explained, or not explained, discussed with you. Angular magnification. We have discussed this in the previous slide, where we said more is the height, or more is the height of an image, more is the magnified image, more is the vision angle that you create. So let's first write the formula for magnification. M is given as vision angle made by final image. Now you will ask me, sir, we are having one lens. Why are you using the word final image? Because this will help you to process the formula for compound microscope also. Final image divided by vision angle made by object when kept at D. First, we'll understand this formula. Write down vision angle made by final object, final image, divided by vision angle made by object when kept at D. When object kept at D. Let's first discuss about the denominator. Okay, for that I'm going to the previous slide. So let's go to the previous slide. Okay, no, not that. I'll make one. So let's see the denominator part. So in order to appreciate the denominator, I have There's some work going on. Some work going on, right? So let's say now your object is at D. D means what? See, the better word is, let me write it like this. When the object is kept at D means this distance is D. Is this understood? And this is the height of the object. And this is the vision angle, that's the denominator that we're talking about. Now, this is something, children, that is frozen. You will be able to keep the object at D means this is a simple formation which we cannot alter anything out here. This angle we can call as alpha, and this angle we call as beta. Is this understood? So let's try and have a relation out here. This is my alpha. My alpha always remains constant. Just try. Tan alpha will be equal to HO by D. Have we understood? Okay. And alpha being small is just a relation that we are taking. Tan alpha is approximately equal to alpha. So based on this, we can say alpha is equal to HO upon D. Now try to understand, children. What does a microscope do? What does a microscope do? This formula will help you understand. A microscope is first trying to get the image when the object is placed at LDDV. At LDDV, as a person, I can see the biggest object. Microscope is going to magnify. What is the input to the microscope? The object size is the input. So please give an object size which is the maximum. How do you give the maximum object size when the object is at LDDV? That is this. This object is being magnified by an image which the microscope is trying to create. Understood? So let's go back to say this particular diagram. Now, how do you work on beta? My beta will be the angle created by the final image with the eye. Agreed? Now your eye is, this is how you are seeing this. So whatever you are seeing from here, can we say that this angle is beta? We can say that. Final image created with the eye means this arrow, this will be going with the eye. If this is beta, don't you think this is also beta? Right? So I can actually say tan of beta is HI by this, or tan of beta as HO by this. Now, how much is this distance? This is the object distance. This distance is the object distance. Do you agree or not? And the object distance I am mentioning as UE. Now you may say, why did you put an E? Keep it. It will help me in compound microscope. You think that E stands for the eye. Simple like that. Okay. So beta, tan of beta can be expressed as what, beta? Now tell me. HO upon UE. Tan of beta is equal to HO upon UE. That means beta being small, because it's a hand lens, everything will be very small. Beta being small, tan beta can be approximated to beta. So beta's value becomes equals to HO by UE. Is this clear? Right? And now I come back to my magnifications formula, which is M is equal to beta upon alpha. And beta upon alpha means, how much is beta? HO by UE divided by HO by D. Clear? So M becomes equals to HO by UE into D by HO, which is equal to D by UE. Which is D by UE. This is the basic formula of magnification for an object by a simple microscope. What is magnification? Magnification is equal to D by UE. D is what? 25 centimeters. UE is what? UE is the object distance. Are you understanding now? Okay. Now this formula we have to appreciate in two cases. We just found out that magnification is beta upon alpha, and we found this value as what? D upon UE. Have you done till this much? Is it clear? No dispute? Okay. Now, there are two conditions. One is for maximum magnification. For maximum magnification. For maximum magnification, the image must be at 25 centimeter. Whatever image you create, or I say the image must be at D. Don't you think? The image must be at D for maximum magnification. That is, maximum magnification means where I see the biggest image. Where do I see the biggest image? When the image is formed at D. Agreed? So I just apply the lens formula out here. 1 upon F is equal to 1 upon V minus 1 upon U. Agreed? In this criteria, there is another thing. When you're trying to see something at 25 centimeters, whether it's an object or an image, your eye also becomes like this. After some time, your eye will pain. So this is always called strained or stressed vision. This is the strained eye. Strained, or you can also say the stressed vision. Although you are seeing the maximum size, but your eye is strained or it is under stress. Clear? The opposite of this case will be relaxed vision. We all love to see something in relaxed vision, right? So in this criteria, what about for this formula, the U is always the UE, but UE is measured on this side. Don't you think the U is negative of UE? Right? And what about the V? The V is B. That is at D, but D will be negative because you are measuring on this side. Arjun, clear? Try to put this on this formula. This is F, means this is the focal length of the hand lens that you are using. So 1 upon F becomes equals to 1 upon negative D minus 1 upon negative UE. Clear? Which means 1 upon F becomes equals to 1 upon negative 1 upon D plus 1 upon UE. Clear? Or from here I can say 1 upon UE is equal to 1 upon F plus 1 upon D. Correct? Now what was my formula for magnification that I got? Magnification was given as H. No. D by UE. Now instead of UE means 1 by UE. You substitute this value of 1 by UE. This is UE. Okay? This is UE. So I can write M is equal to 1 upon F plus 1 upon D multiplied by D. पक्का? ये डाल दिया वहां पे. So my M becomes equals to D multiplied by D will be what? This will become 1. 1 plus D by F. This is the final formula for magnification for strained vision. What is the magnification of a hand lens? The magnification of a hand lens is always D by UE. What is the maximum magnification? This is the maximum magnification. This is maximum magnification. Alright, children, just apply your common sense. You are adding a factor of 1. 1 as a factor got added. So this is much more magnification. Right? My next criteria would be to find out the magnification for relaxed vision. Okay, two, for relaxed vision. Relaxed vision means, what do we mean? And when your eyes are relaxed, what is the maximum you can see? Infinity, we say. Not necessarily that everyone is able to see till infinity, but we assume that our far point is still infinity. So in this case, I would again use the formula 1 upon f is equal to 1 upon v minus 1 upon u with my conditions. My u still is negative of ue, but my v has now become negative infinity. Right? Infinity or negative infinity means the same. So my 1 upon f becomes equals to 1 upon negative infinity, which is also same as infinity. So this is infinity minus 1 by negative ue, which is 1 upon f is equal to 1 by ue. Agreed? 1 upon infinity is 0. So now what was my magnification formula? My magnification formula was d by ue, and my d by ue now becomes equals to d by f. This is relaxed. Now just compare between relaxed and maximum. In maximum, a 1 factor gets added, and in relaxed, it is just d by f. So children, don't confuse here. If somebody tells you what is the magnification for a hand lens, the magnification for a hand lens is always d by ue. Do put your signs in proper manner. What is the maximum magnification by a magnifying lens? 1 plus d by f. What is the relaxed vision magnification or relaxed vision? It will be just d by f. What's the difference between the two? The difference between the two is simple, that one is more than the other and it has a plus 1 factor added to the magnification. NCERT, I think, writes up to 9 times. It doesn't go up to 9 times. It's like 4 or 5 times magnification by hand lens, not more than that. Fine. Now, simple microscope has only one lens. We go into compound microscope. Now, compound microscopes, the one type we study in our syllabus is showing you only 2 lenses. But actual compound microscopes might have 16, 17 lenses because they produce very, very high magnification. Like a tiny paramecium will be seen this much sole like paramecium that you are able to see. So can we go to compound microscope first? So let's first draw the diagram for a compound microscope. A compound microscope has got, and draw it just in this order that I am drawing. It will make it easy. It will be easy for you. A compound microscope has got 2 lenses. The first lens is known as the objective, and the objective will be a lens whose focal length will be small. It will be a short focal length. Okay, smaller focal length. So its convergence will be more. This is my objective. So this is known as my objective. It is near to the object, so it is known as my objective. It will have a short focal length. So let's say that its focal length is here and this is the focal length. When you have a short focal length, why are you making the focal length shorter? You're making the focal length shorter so that whichever object you bring near it or you focus this on, the object should be beyond the focus. So beyond the focus means it will be at a position between f and 2f, right? And between f and 2f means you will always create what? You will create, the image will be created beyond 2f and it will be larger in size. So let's try to draw the ray diagram for this. Now, 1 minute, children. This is FO, this is FO dash, right? And let's put the image, sorry, object. This is my object. So a ray of light which is parallel to the principal axis will pass through the focus. Perfect. And a ray of light which is passing through the optical center will actually go undeflected. Fine. This is height of the object HO. And let my object be classified with AB as its credentials. So I will create a I will create a real, inverted and larger than object image, the magnified. Very good. So this would be my image. And my image credential now will be A dash, B dash. Right? This now creates the scenario for my second lens. My second lens would be here. And my second lens is such that it will have a larger focal length. The objective will have shorter focal length. And the second lens, which will be known as my eyepiece. This is my eyepiece. My eyepiece will have larger focal length. Eyepiece because your eye is on this side and this has larger focal length. In fact, if you would appreciate, the eyepiece is now going to behave as a simple microscope, so that the image of this one becomes an object for this, and by default the focus will be beyond the object. So it creates a case of object placed between optical center and focus. So let's just mark it. So let's say somewhere here is the focus. This is the FE and this is FE dash. Right? So let's continue our ray diagram once again. Now a ray of light which is parallel to the principal axis for this will pass through the focus. Okay, bacha? Understood? And another ray which will be passing through the optical center goes undeflected. Acha, try to understand what is happening. The image created by the eyepiece, the objective, becomes the object for the eyepiece. And if I actually blank out this part, this is just the same drawing, the previous case diagram, just that the object is inverted. Fine. So these rays will be divergent rays. These are divergent. So what I'll do, I'll pull them backwards. Right? And now the image that will be formed would be a virtual image. And let me give a nomenclature to it. This will be A double dash, B double dash. Clear? Fine. Some more namings we need to do. So this is the initial object distance. This is image distance as seen for the objective and this is object distance as seen for the eyepiece. Although this is not required, but still, let's keep it. And let me start filling it. This is UO. This is VO. This is UE. And this is VE. Clear? Namings are clear? Okay. So we start with compound microscope. A compound microscope consists of two lenses. The one which is near the object is known as the objective. The one that is facing your eye is known as the eyepiece. Your eye is here. Your eye is here. The one that is facing the eye is known as the eyepiece. The objective has a shorter focal length deliberately, so that wherever you focus it on the object should be beyond the focus. As a result, you will create the first image, which will be a real inverted magnified image. And that real inverted magnified image will serve as the object for your eyepiece, and your eyepiece is deliberately a lens with a larger focal length, so that the object gets, the image of the first, which is the object for the second, gets placed between the pole and the focus, creating the scenario for generation of a virtual erect magnified. Achha, this is an erect image, by the way. Why? Because the object was also erect. So this is an erect image, huh? But but if you compare it with the initial object, then it is definitely an inverted. So if somebody tells you microscope produces an erect image or an inverted, what you will say? It produces an inverted image. Microscope produces a inverted image because originally your object was this. It has produced an inverted image. If you want the image to be straight, later on you can have some reflecting mirrors inside. So let's start with our magnification formula. Magnification, same, vision angle made by final image divided by vision angle made by object when kept at D. Object kept at D, which will be known as beta upon alpha, right? Alpha, there will never be any change, so the alpha remains same. Alpha, can you see alpha by your eyes closed? HO, and there is a what do you call object distance, which is D, right? So alpha would be, if you again want to do it, then you can draw, but I think that will be just, I know, spending time. You want me to draw that once again? When the object is kept at D, so this is your eye, sorry, this is your eye, and this is the object. Height of the object is HO, this distance is D, and this angle will be your alpha. So the same problem, tan of alpha, tan alpha will become equal to how much? HO upon D, which means tan alpha is approximately equal to alpha, so alpha is equal to HO upon D. No change in this. Let's have a look at beta now. Tan of beta. Now, what does beta say? Beta says angle formed by the final image. So this is the final image and image distance, but this angle is same. We can consider this part also. So what is this part? This is my A dash B dash, and this is UE. Agreed, children? This is beta, right? So tan of beta can be now written as A dash B dash divided by UE. Clear? But this UE is creating problem for us. We need to abolish this UE. So how to abolish UE? Come again. Just look at this lens. Just look at this lens. Not this lens, this lens. Let's just look at this lens. Think it to be an independent lens of your grade 10 case. In grade 10, we did not have this part, right? We did not have this part. We just had this part. Agreed? So let's go to grade 10 and we say for objective magnification would be equal to V upon U for the objective.
Yeah.
Can you, and let's go by the sign, because it's an inverted, negative has to come. So what is the V? V0. But V0 you are measuring on this side only for this lens. A positive V0 divided by a negative U0. Yes or no? However, magnification is also equal to height of image over height of object. The image is slanted, so it would be a negative A dash B dash divided by height of the object HO. Do you agree? This is grade 10 formula here. Just for this lens. This is its image. See, our job is to abolish A dash B dash. So the minus cancels minus from here, and A dash B dash can be now written as HO VO divided by UO. Are we all fine? Right. Very good. That means beta is equal to A dash B dash by UE, and now instead of A dash B dash I can write HO VO UO UE. Did you understand this? Now I have to go to second page, no other option, so please note down. Arjun, okay? HOVO UO UE. Okay. So M is given by beta over alpha, where beta is HOVO and divided by what? UO UE divided by HO by D. Clear?
Yeah.
Okay. Going further, my M becomes equals to HOVO UO UE into D by HO. Clear? HO cancel, and a bit of rearrangement gives it like this: VO by UO into D by UE. Isn't VO by UO the magnification of the objective? Yes. And isn't this the magnification of the eyepiece? Yes. Abhi to you have derived this, na? That the magnification for a single hand lens is this. So the magnification of a microscope is given by the product of the magnification of the objective multiplied by the magnification of the eyepiece. However, our job still remains stressed and relaxed vision. For strained vision, that is maximum magnification, you will get the same answer. Instead of this, it will only get multiplied. What was the maximum magnification that you got? 1 plus D by F. Here it will be 1 plus D by F of E, it will come. So let's see that for maximum magnification. For maximum magnification, where should be the image? The image should be at D, right? So you apply the formula, the image should be at D. So 1 by f is equal to 1 by v minus 1 by u. Okay, u is what? U is equal to ue, but ue is measured in what way? That is the maximum magnification. Children, see, maximum magnification means you have to see from this lens perspective. From this lens perspective, for this lens perspective, ue will be negative. Okay, what will be the value of v? The value of v will be negative d, right? And do you have a book with you? Just check one thing. Can you just 1 minute? Let's just put small thing. Just a minute. 1 minute. Yeah, magnification of the eyepiece. Magnification of the eyepiece. Yeah. So for strain vision, U will be UE, that is negative UE, right? So my equation now becomes 1 by FE is equal to 1 by negative D minus 1 by negative UE. So it gives me again 1 by UE is equal to 1 by FE plus 1 by D. Correct? So punch that out here. So my magnification, maximum magnification becomes MO is retained as MO, and instead of D by UE, this becomes 1 by FE plus 1 by D into D. So MO into sorry, it will be 1 plus D by FE. Same, just you get a maximum. Just the eyepiece value. The same thing comes here. And for relaxed vision, U is equal to negative UE, V is equal to infinity, and so it becomes 1 by F. Same thing. V by FE. Right there. Yeah. VO by UO. Okay. One more thing. Where is the microscope diagram gone? This. Where did it? Yeah. So and this length, this is known as length of the microscope given by VO plus UE. This is known as length of the microscope. When you are talking about length, then we will be using absolute value. Length has nothing to do with plus and minus. We will just take the absolute value. Our next topic is actually theory, so we won't talk that much about it. It's about telescope. You can also read. I mean, there is nothing. There's no what do you call? There will be no derivations out of this. What does a telescope do? A telescope never magnifies. A telescope brings far distances. Tele is brought under your scope. Telescope never magnifies. You see Jupiter this much. Jupiter is not this much. Jupiter is much bigger than this. Okay. So a telescope will be just opposite to that of a microscope, in which the first lens that we will have, the objective of the telescope, objective will have large focal length, a large f. But no matter how much large f also you have, your object will be always beyond your f, no matter how large your f may be, because the object you are trying to see is far, far off away. So this is there in your book also. I'm just trying to make the diagram. So you'll have a large, so this rays will be coming from far off distance, and now here the focus is quite far away, so we don't have something called a focus, but we will have something called a focal plane. Say this is my focal plane. Okay, this is my focal plane. So the rays are coming from far away and they will be parallel. So a ray comes from here. Now this ray will not go and meet at the focus, but it will go at the focal plane. And similarly, from the focal plane, there will be another ray which will be parallel to this. So, one. So this is a distant ray which is coming undeviated from the optical center of the objective, and then you have another parallel ray which is coming, and this ray will now not meet at the focus, but it will meet on the focal plane. This we had discussed in grade 10, if you remember. All parallel lines need not be parallel to the parallel rays need not be parallel to the principal axis. So you will be creating your first image out here, and this image would be a real and a inverted image. We used to say that this used to be the case of when object is placed at infinity. So we will have Gaurav in class. I'll call you later. No problem. Okay. It's okay. So objective, and this is large f, which has a large f. It will create your first image. And now we will have our eyepiece. Our eyepiece is so designed that our eyepiece will be a shorter focal length. Okay. So this will be my eyepiece, which will be a shorter focal length, so that deliberately this first image goes and gets settled. This will be a shorter focal length, and yes, this is exactly the focus of the eyepiece. If you place an object at focus, where do you get the image? At infinity. Okay, this is exactly at the eyepiece focus, Fe, and this is Fe dash. And so my next ray would be passing from here, which actually should be parallel. Okay. and then we show it. Image is formed at infinity. This is the criteria. Anyways, for you, the okay, couple of discussions out here. And here the magnification is given as the magnification for a telescope. Magnification for a telescope is FO divided by FE. Yeah, just check the book. It should be FO divided by FE. Just check the expression for magnification of a telescope. It should be FO by FE. Right? It's FO by FE. Couple of things which you should know for theory questions. In a telescope, the image that you will be getting will be always an inverted one. Right? Real telescopes or binoculars will have correction mirrors also. So the mirrors will actually correct this particular image. In order to sorry children, I'm also getting in there. These lenses are very big, and constructing these lenses are very difficult. As a result of which, lenses, how do you hold? You can only hold them on the rim of them. So mounting, handling becomes very difficult. So all these astronomical telescopes which we use for hobby purpose also will now have a mirror. So you will have a concave mirror. The concave mirror's job is to get all the rays. The same thing. You will get all the rays, distant rays, and you will create first an image which will be inverted. And then you will use an eyepiece to actually magnify the image created by the concave mirror. Those are known as reflecting telescope. This is a refracting telescope. Now, once you enter a mirror inside the telescope tube, you are again reducing the amount of light that will come to the eyepiece. So what they did, they again created, if you see in your textbook, they created one more convex mirror inside it. Means